This problem is very much like the one that I did previous to this. It's essentially the same problem. The only thing that we're going to discuss here is that now we're looking at his rowing speed is v1, his walking speed is v2, and the angles that he travels at form outer angles or exterior angles, theta 1 and theta 2, and that when we satisfy this condition here where the sine of theta 1 over v1 equals the sine of theta 2 over v2, when that condition is satisfied, we get a least time. So all we're going to do to verify this is we're going to simply go back and consider the same exact source that we had before, and that's going to be, we just start off with, same thing, find out the individual times, add them together. That's the total time it takes. And so we're going to go ahead and take the time, t1 here, is going to be equal to the distance traveled, which is the square root of the sum of squares on the lengths of the triangle divided by its rate, which is v1. And on the second side here, we're going to take t2 is equal to, now I've already done this here. This is the expansion of 3 minus x quantity squared. So if I take, and my distance traveled is a square root of the sum of squares, and so if I add 1 to that, then I get x squared minus 6x plus 10. And that's divided by v2, the rate that he's traveling at. And so let's express t as the sum of our two times here. And when we do that, we get the square root of x squared plus 4 over v1 plus the square root of x squared minus 6x plus 10 over v2. Now, before I get too much further into this, I did want to point something out. We're going to have to use a little bit of geometry here. And in geometry, if you recall, if you had parallel lines, like we do here and here, then the alternate interior angles are the same. And so this is going to be theta 1. This is going to be theta 2. I just kind of want to point that out so that we don't get lost later on. Because signs, the signs are going to kind of fall out of this, but you have to be paying attention for them. All right, so now proceeding along here, we are going to take the derivative with respect to x. The derivative with respect to x is equal to, now we have to take the derivative of this, which is going to be 1/2, and so our v1 comes down, and then our root comes underneath, times the derivative of what's inside the root, which is 2x, plus, do the same thing here. There's a 2 that comes down for the 1/2, this is for the power rule. The root comes underneath, this is also for the power rule. But we take the derivative of what's inside, and that's 2x minus 6 goes on top. Canceling things out that we can, we notice that this cancels to x minus 3, and that takes the 2 out of there. And so we get 0 is equal to x divided by v1 root x squared plus 4 plus x minus 3 over the square root of v2 times the square root of x squared minus 6x plus 10. Okay, so now that we've got that, we want to go ahead and take a look at what this is. So now, if we look back up here, we see that if we take the sine of the angle, it's the opposite, which is going to be x over the hypotenuse, which is going to be this thing here. But the hypotenuse, remember, is a distance. So it's just going to be that root x squared plus 4, which is this here. That is equal to the sine of theta 1. All right, now we're going to have to use a little bit of knowledge here and consider this to be the 0 point if you look at theta 2, the opposite is going to be 3 minus x, and the hypotenuse is going to be this x squared minus 6x plus 10. And so now we have x minus 3 and 3 minus x. That's the negative of one another. And so this is going to equal the negative of sine. Because the top is negative of that, of what we're looking for, we need 3 minus x. This is x minus 3. To reverse the order of differences, we take the negative. And so this is going to be that. So 0 is equal to sine theta 1 over v1 minus sine theta 2 over v2. And that's where you get sine, if you solve for just throwing one on one side and one on the other, you get sine of theta 1 over v1 is equal to sine of theta 2 over v2. Okay, well that's fine. But now how do we know that that's a minimum or a maximum? Well, you can take the second derivative if you so choose. And if you do that, then you take, we can set, oh man, my eyes are itching this late at night. You can go ahead and take the second derivative with respect to time, or with respect to x. And so if you do that, then you get the d2t over dx squared is equal to now the derivative of the top times the bottom, and so this is x root x squared plus 4 minus the derivative of the bottom, which is the derivative of the bottom is going to give us this, and this is going to be v1 by the way. I'm just going to take this 1 over v1 right outside. The derivative of the top times the bottom minus the derivative. The derivative of the top is 1, goofball, times the bottom minus the derivative of the bottom, which is going to give us over 2 x squared plus 4 times the top, but times the derivative of what's inside, which is 2x squared. Minus, and now the 1 over v2 comes out. Oh, plus, sorry. I haven't minused it yet. And this is going to be the derivative of the top, which is 1, times the bottom. So you have the square root of x squared minus 6x plus 10 minus the derivative of the bottom, which of course, again, is 2 root x squared minus 6x plus 10 times the derivative of what's inside times what's upstairs, which is going to be this x3, times the derivative of what's inside, which is x, 2x minus 6, times the top, which is x minus 3. Okay, so now if I do this out, okay, and so now I have 1 over v1. So if I work on this here, now x, remember x has to be positive. And so we got to figure out, well, this has got to be positive. If this is not positive, then we have some serious issues. Well, we got to get this down into something we can see. At this point, I would probably just go back and put this in my calculator, throw ones in here for v1 and v2, and just let it be. If I multiply both sides by v1, v2, then effectively I can just kind of ignore it. But okay, let's just go ahead and see if we can't find a way to do this here. So we've got x, we need an x squared up top, and so, or a 2x squared on top. So we have to multiply by this on top and bottom over here, and so that's going to give us 2 times x squared plus 4 minus 2x squared, and this gives us all over 2 roots x squared plus 4, 1 over v1 plus 1 over v2. And this is going to give us 2 times that, and so this is going to give us 2 times x squared minus 6x plus 10, Let's see, minus, oh, we should probably just do this. Yeah, we don't need this 3 here, or this 2 here, I mean. And then we're going to say minus x minus 3 squared all over x squared minus 6x plus 10. Now from above, you'll remember that this is just this minus 1. Let's take a look. Oh, all right, it was this. And so we added 1 to it to get the 10. And so when we subtract it back off, we're just going to get the 1. And so this is going to equal 1 over v1. The 2's cancel. Let's see, so this is going to give us 4 over root x squared plus 4 plus 1 over v2. This is going to give us 1 over x squared minus 6x, goofball, minus 6x plus 10. There we are. Okay, so now we're only considering the point where x equals 1. Because remember our x value was 1 when it solved for the when it solved it for the least time. We had 1 mile here before. And so if we just plug this in, then this is going to give us 1. This is going to be positive. This is going to be positive because this is going to be 1 minus 6 plus 10, which is going to give us a positive 5 on the bottom. And so v1 and v2 being positive, this is going to be all greater than 0. So our second derivative squared is greater than 0, which implies that we have, in fact, a minimum, a relative minimum by the second derivative test. Not the easiest thing in the world, but very doable. You just got to keep in mind where you're headed. Now you could have looked at this a little different way and checked the endpoints and made sure that this was in fact a minimum. Use the first derivative test. That would have been fine. This is just an example of using second.